bit more about signal to noise ratio that we'll be using because we'll actually go and look at the experiment in a bit, but one of the experiments is 2-slit interference, 1 photon at a time. It's really cool. We'll actually be seeing the results of photons on some level passing through both slits, interfering with themselves, but you detect it as a discrete event. And so we actually see an interference pattern, even you send 1 photon at a time to a pair of slits, and you're going to be counting them using a photomultiplier tube, wherein it's under high voltage, and a photon ejects an electron from a cathode via, anybody know what that would be? It's the effect. Remember that from like 280? Photoelectric effect, yeah, so it ejects the electron via the photoelectric effect, and then that electron will be accelerated by a positive potential to another metal plate called a dynode, and that's designed after the electron's accelerated, it will have way more KE than the work function for the metal, and it will actually eject multiple electrons, and then those will go to the next dynode and the next dynode. So you get this cascade of electrons so that you get a macroscopic signal from a single photon event. And so it will count every time that the photomultiplier tube registers a photon. So with something like that, there's also dark current, so to speak. In other words, sometimes you get electrons that come off of the cathode and a photon didn't cause it, it's just noise, essentially. And so you'll have a background that you have to subtract. It's similar to if you're measuring radioactive decay from some source. Well, some counts are just from the room or from your body or whatever, because everything is radioactive, at least at a low level. And so your signal also has noise in it, also has counts that are there, not because of actual detections of the thing that you're observing, but because of background noise. And so let's talk about how you handle that, how you would figure out what the signal to noise ratio is in the presence of background. So off we go here. We said last time, as a reminder, that if every count was a genuine detection, if there was no background noise, then for counting statistics, the SNR, the signal to noise ratio, which is the reciprocal of the relative error. It's the relative error is the uncertainty divided by the value of the quantity. Signal to noise ratio is just the reciprocal of that. Instead of being the ratio of kind of noise to signal, it's signal divided by noise. So in this case, if we had S signal counts, and they're all genuine, and again, we did this last time, but it's been a while when you have these 2 days a week classes, and they're all genuine, they're all real detections, then the signal to noise ratio would be the number of signal counts that you got. And then for Poisson statistics, what's the standard deviation for Poisson statistics? If S is the number of counts, then you expect the standard deviation, if you do the experiment many, many times, find the standard deviation for Poisson statistic. Sigma sub S would be what? Square root of the number of counts, right? So S over the standard deviation S would be expected to be S divided by the square root of S, or in other words, the square root of S. So the signal to noise ratio is the square root of the number of counts. And I think we said this last time, but repetition is the key to learning. The signal to noise ratio, hey, be nice to me, chalkholder. The SNR, the signal to noise ratio, increases as S increases, but only as the square root of S. That just does nature of reality for our counting statistics. A little bit of a frowny face there. You need to quadruple the counts to double the signal to noise ratio. And again, that's where we get this diminishing returns. Because if you want a 10 times better signal to noise ratio, why, you've got to get 100 times as many counts. If there's a given count rate, you need to count for 100 times longer to get a 10 times factor of increasing signal to noise. So after a while, it just ain't worth it anymore. Questions at this point? What questions do you have? So think of our photomultiplier too. If every count was a genuine photon coming through the instrument, then this would be our signal to noise ratio. It would just be however many counts you got, and you'll see that you'll be in the order of like 8,000 or something like that, depending on where in the pattern you are. So the signal to noise ratio in this ideal situation would be, in that case, square root of 8,000, whatever that is, which would be pretty good. Okay? Now, often we're interested in the counting rate. How many counts do we get per second, per minute, per whatever? Often we're interested in the counting rate per unit time. And that reminds me of a pet peeve of mine. I don't know if it's a pet peeve of yours. I've seen so many interviews with policemen talking about like speeders, or they're doing an accident report and they talk about, well, they were moving at a high rate of speed. It grinds me a little every time I hear that, because speed is a rate. So a rate of speed is like a high rate of the rate of change of position at the time. Anyway. They need to get life. There are more important things to worry about. Counting rate per unit time, which we could say, well, that's R sub S, is number of counts. Change the number of counts you get over change in the time interval. If we count for time t, and observe S counts, okay, somebody's playing a video, I think, next door, so let's see if I can at least partly cut down the sound by closing the door. And observe S counts, then the count rate, R sub S, would be S over T plus minus sigma sub S over T, for including the uncertainty. And so the uncertainty in S divided by the time interval would be the uncertainty in the rate. So that'll be S over T plus minus square root of S over T is how you would report your result. We are assuming here that the uncertainty in the T measurement is negligible, which typically, if you got a good timer, then that won't have very much uncertainty with it. Otherwise, we'd have to error propagate the ratio of S over T and include a factor for the uncertainty in the time interval. Usually, though, your timing is much more precise than the signal to noise ratio. Your delta T over T, well, I should say, your sigma T over T is generally a lot smaller than the sigma S over S is, and so you can usually ignore that. So here we assume that the uncertainty in T is negative. in the experiment, you'll be counting for 10 seconds at a time, negligible, 10 seconds at a time, and yeah, that would be plus or minus some tiny fraction of a second. So then we can note that the signal to noise ratio, remember that's the square root of the number of counts, but the number of counts is the rate, the counting rate times the time, and so it grows as the square root of time. In other words, you need to count 4 times as long to double the signal to noise ratio. Or 100 times as long to improve it by 10 times, and so forth. Stop making that noise. So again, it's the whole, diminishing returns thing. You have to count longer and longer to get improving signal to noise ratio, and eventually it's just not worth it anymore because everything has an opportunity cost. What other exciting research could you be doing instead of spending that time getting more counts? Questions, comments, observations? So as an aside, which would show up more when I'm teaching this as Astronomy 345, but if you take a digital image, you're counting photons there too. All those pixels, they're counting photons in the digital image. And so again, you'll have fluctuations related to how many photons came in, but you also have dark current in an imaging chip as well, a digital imaging chip. You get some electrons in the pixels that aren't due to photons, they're just due to thermal noise within the detector. And so when you take a photo, in a night scene, it looks grainy, and that's digital noise. That's counts showing up in the pixels that are not due to photons. And often, when you have a night mode, the camera will do pixel binning, where they'll add adjacent pixels together, and it lowers the resolution a bit, but it improves the signal to noise ratio. The image looks less grainy. And like in my phone, and this is becoming more and more common, the main sensor is 108 megapixels, but when I take an image, generally it cuts it down to 12 megapixels by binning pixels together. And that's because you get a better signal to noise ratio that way, and because also 108 megapixel images start taking up a lot of storage space very fast. So back to our story here. Now suppose that in addition to our signal counts S, that there are also background counts B, the noise background. How are we going to account for that? In addition to our signal counts S, there are background counts B. So our measurement is going to be S plus B now, right? The ones that are genuine signal counts and the ones that are just background noise. Now they don't come with labels. You don't know which individual counts are signal counts, which individual counts are background counts. But on the other hand, if all you want is the number of signal counts, well, then it would make sense to make a measurement where you're not exposing the photomultiplier tube to any light, and count how many counts you get then. And then you can say, okay, well now that's my background count rate. Maybe I can just subtract that from my signal count, from my measurement where I've exposed it to light, and that should do a good job of subtracting off the noise and giving you a good idea of what the signal count by itself is. You can't identify individual counts as signal versus background, but you can do a good job of correcting to get what you think should be close to the actual number of signal counts. So our measurement will give us S plus B counts. If we measure B separately, by not exposing the detector to the source, then we can get a better estimate of S by subtracting the measurement of the background alone from the measurement of the source plus the background. We can get a better estimate of S by subtracting the measurement of the background alone. And physicists do this all the time in counting experiments and in other contexts as well, where there's some background that you're trying to account for. By subtracting the measurement of the background alone, from the measurement of the source plus background. So we can say S sub t, where that t doesn't stand for, well actually I'll just write it down. S sub true, so in other words the true amount of signal counts. Well, that should be approximately equal to, you're going to use a slightly funny notation here, S plus B minus B. And I say approximately because if I measure the background, am I going to get the same result every single time, the same number of background counts every time I measure? No, because like anything else, there will be statistical fluctuations. And so this isn't going to be perfect because when you took your measurement, there was some unknown number of background counts in the measurement, and then you measure the background, and that's generally not going to be exactly the same as the number of background counts in your measurement. So this won't be perfect. These two B's won't be the same thing. My funny notation is I'm saying B in both cases, even though they really mean during the measurement and during the measurement of nothing, when you're not connected, trying to look at the source. So this is my S plus B. That's measured value of signal plus background. And B up there is the measured background. And I should put a notation note, say what I was just saying about how I'm not going to bother with saying S sub measurement and S sub not measurement or whatever you're going to call it. I'm sorry, B I meant for that. In other words, I'm just using the same symbol B for just background counts in general. You kind of think, well, maybe B is, you're thinking that's a typical value, something like that. So notation note, the background counts are both represented by B here, but they will generally not be equal due to statistical fluctuations. Which is why it's only approximately true that the true signal is the measured signal plus background minus the background. Notation note. So Dr. Unemacher probably would like this, but that's okay. The background noise counts are both represented by B here. But they will generally not be equal due to statistical fluctuations. But I think it'll be clear from the context that we're going to read by it. Questions, comments, observations? So those background counts that are contaminating your signal, causing you to overestimate, if you didn't account for it, overestimate how much signal there is, do those background counts represent a random error or a systematic error? Systematic. It's systematic, right, because every single measurement is going to be influenced the same way. They're all going to be systematically increased above what they should have been. So even though the background noise is random, it's still a systematic error. And doing this subtraction then is accounting for and reducing the systematic error. Cool, we've improved our measurement by accounting for the systematic error. But it's important to note that everything has a price, because every time you do something like a subtraction of a measurement and so forth, you're still going to have random errors in that. So in other words, while we're reducing the systematic error this way, very much worth doing, we're increasing the random error. But it's worth paying that price. So let's make that all specific. We have decreased the systematic error in S by subtracting off the background. Decrease the systematic error in S by subtracting off the background. But it comes at the expense of adding random error. Totally worth it, but nevertheless, it does add random error. expense of adding some additional random error. In astronomy and in other imaging, where you want to take images where you should subtract off the dark current noise, we do exactly that. We take images of the sky, and at big observatories, they can cool their imaging chips with liquid nitrogen. And that virtually eliminates the dark current. They don't necessarily have to bother with this. But if you're not using liquid nitrogen, and I sure as hell don't, that's difficult, you take an image of nothing, and that's called a dark frame, where it's just an image of the noise, and you subtract that pixel by pixel from the light frame. You take an image of the actual thing you're trying to photograph. And so we're doing exactly the same thing, only we're doing it for every single pixel, as opposed to with a photomultiplier tube or a Geiger counter or something like that. That's kind of a one pixel device, if you will. And so you're just doing it for that one measurement, as opposed to the millions of measurements that you're making when you make a digital image. So we have to error propagate S plus B minus B. So what we can say is that sigma S squared is equal to, we'll call it sigma S plus B squared plus sigma B squared. And I'm using a little b now just to kind of, well, I don't know why. The source I base this on used little b, so I'm just going to do that. I could make it a big B if I wanted to. If you want to make it a big B, go ahead. But anyway, so that first term is the variance, which of course is the uncertainty squared, in S plus B minus B. The thing that we're looking for is what's our uncertainty in our estimate of S true. Sigma S sub B squared is the variance in S plus B. And the last term there is the variance in B. That's the term that is the extra random error that we're adding by doing the subtraction. If we didn't do the subtraction, we would just have sigma S sub B squared. But since we're doing that subtraction, we have to include a term in our error propagation for that second term there. And when you subtract quantities, the variances add directly together, right? And so that would be the uncertainty in S plus B minus B would be the uncertainty in B squared minus the uncertainty, the uncertainty in S plus B squared minus the uncertainty in B squared. And uncertainty squareds are variances. Does that make sense? What questions do you have? Well, we can figure out what these are because it's all counting statistics. And so the golden rule of counting statistics is that if I get S plus B counts when I do my measurements, and that's a Poisson random variable, then what is sigma squared for S plus B? Or put another way, what is sigma itself for S plus B? What's sigma squared for S plus B? If I have S plus B counts, and it's a random Poisson statistical process, what is its variance? The variance in Poisson statistics is what?
Square of S plus B.
So that's the sigma. That's absolutely right. That sigma is that. So the variance is S plus B itself, right? In Poisson statistics, the variance is equal to the mean And the uncertainty, the standard deviation, is the square root of the v. So, in other words, if the background is also described by Poisson statistics, that's using the case. Those are just random counts coming in too. So with the caveat, usually true, that if the background is also described by Poisson statistics, then we have that sigma squared of s plus b, well, that's just s plus b. And sigma squared of b is just b, because if you got b background counts, Poisson background counts, then its variance is b. And this says that the variance in S should be S plus B plus B, right? S plus B for this term, B for that term. So it's S plus 2B and not 2B. S plus 2B. So that tells us the signal to noise ratio. Signal to noise ratio is going to be equal to S over sigma S. Well, that'll be S over not just the square root of S, but the square root of S plus 2B. You'll use this with the PMT. You're going to do exactly what we've been talking about. You're going to measure background counts and subtract that off, if you will, from the true count, or from the measured counts in order to estimate the true counts. So the signal noise ratio won't just be S over the square root of S, it'll be S over the square root of S plus 2B. The background is lowering the signal to noise ratio because in addition to noise that's just fluctuations in Poisson statistics, you've got additional noise, which is background counts. Questions, comments, observations? All right, let's take our break. Let's take a field trip. We're going to go look at the instrument with the photomultiplier tube that I've been talking about. So, I'm not sure how well this will work for the video, but come with us, Esmeralda, as we go down the hallway.
Charge the battery pack. Yeah, okay. Let's see. Okay. Yeah. I don't know how well you'll be able to see this, Esmeralda. I'll probably zoom in a bit. So actually, I should come over to this side, really. So here's the two-slit interference experiment here from a company called TeachSpin. They make such charming things. A lot of their stuff is like wooden cases and stuff like that. Here we've got these nice wooden blocks. So we've got this channel. They call it the U channel. It's an optical bench, and there is a single slit that is mounted right here on a magnet, basically. And then here is a double slit on this mount right here, followed by what they call the slit blocker, which is just a wider slit that can block both of the double slits, or block only one of them, or let both of them shine through. And then down here, there's what they call the detector slit. So it's another slit that you can use this micrometer and move it to scan back and forth so that you can measure brightness versus position in the far field diffraction pattern of the two slits. So when you're using the laser, you'll use a photodiode, which is in this doohickey right here. And so it's placed behind that detector slit, and it produces a voltage that's proportional to the light intensity. And so essentially you'll move the detector slit in increments, keep measuring this voltage, and you'll make a plot of brightness versus the location of the detector slit, and that way you'll trace out the interference/diffraction pattern produced by either one slit or two slits. And then later, you'll take the laser out of the path, and there's a light bulb right here that has a green filter in front of it, and it's dim enough that you can calculate that only one photon at a time will be in the channel traveling through the slits and illuminating the detector slit back here. And the photomultiplier tube will be connected to the pulse counter / interval timer, and you'll use it in pulse counting mode, and it'll count the number of detections of photons by the photomultiplier tube, and you'll make a plot of number of detections versus detector slit position, and you'll again see the interference pattern, even though only one photon at a time is going through the slits, and they call that the fundamental, like, quantum paradox of, well, wait, how can a single photon go through both slits? And it's all about wave-particle duality, that sometimes light behaves like a wave, sometimes it behaves like a particle. Roughly speaking, it behaves like a wave in transit, and it behaves like a particle when you detect it with something like a photomultiplier tube. And all we can know is the probability density of finding the photon when we actually do the measurement at any given location. So you get to think about, well, what all does that mean, and so forth. And really, when you get down to it, it really pretty much implies, well, even when you've got a bright light source with gazillions of photons coming through, the interference is really due to every individual photon interfering with itself. They're not interfering with one another, they're interfering with one of them, with themselves, essentially. And I think it's cool that, right here on this relatively simple setup on the tabletop, you can see quantum mechanics like that in action. Now, your whole life is quantum mechanics in action, right? In other words, as far as we know, the universe is described by quantum mechanics, but it's not all the time that it's so explicitly quantum mechanical, so to speak. But the reason don't forget this. The reason I'm bringing you in here is because now we're going to start talking about interference and diffraction so that you know what's happening when you look at this. I don't want it to be just this where you don't understand what's going on and you're just following formulas and so on and so forth. when you're using the photomultiplier tube, and even when you're making the detailed laser measurements in order to avoid background light, that cover right there will be placed on top of the channel, and then we put these things down and it seals it off from external light. But in any case, I'm going to turn on the laser here, and here's this card that you can use to kind of trace things out. And so probably have you kind of take turns, coming up and seeing what's happening here. But you can see here that, oh, look, there's the laser light shining through the slit. If I put it over here, I just see the dot. Here it's shining through shining through a slit they call the source slit that will diffract the light and spread it out so that the double slits are aligned by a relatively uniformly bright field of light. You'll actually do some alignment to try to get it right in the middle of that diffraction lobe so that they're illuminated equally brightly. And so if I place this right here, if everybody can come in and have a look here, you can see the diffraction pattern of that single source slit. In other words, you've got a bright central so-called diffraction maximum surrounded by secondary maxima on either side of it. And we're going to talk about that pattern coming up in the lecture. So, if I come back here, if you come in close, you'll see a pair of strips, a pair of bright stripes, and that's just the laser light coming through the double slits, one stripe for each one. If light always behaved like particles, and those particles had well-defined trajectories, they had definite paths that they traveled through space, well then what you would expect as I move this further and further away would be you'd still just see the two slits, the two stripes, because the photon bullets, so to speak, would either be going through one slit or the other, and so you just see two bright strips corresponding to photons going through either the left slit or the right slit. But in fact, that's not what we see. If I get far away, then down here, I'm going to turn off the light so that you can see this better. Turn this one off, okay. Well, actually what I'll do is, first I'll move the slit blocker so that only one of the pair of double slits is illuminated. So here's the slit blocker. So right now there's two stripes I can see, but if I turn it, then I can block one of them. So now only one of the slits is illuminated. Okay. So as I move back here, then now I get the diffraction pattern of that single slit. So you see a bright central strip and then secondary maxima on either side. So actually come up closer so that you can definitely see it. This is something you really need to be close to see it well, otherwise it's just like taking your word for it, Dr. Harmon, but don't trust me. See it with your own eyes here. I mean, I'm a reliable witness and all, but you should see it with your own eyes. I'm not hearing the ooh-ahs that I was hoping to hear. Ooh-ah. Now I'm feeling a little bit better there. Ooh-ah. Okay. What's going to happen when I move the slit blocker so that both slits are illuminated? Anybody remember? Because I think you did this in, I think, Physics 111, one of the labs. What happens if I illuminate both slits? What do you see?
Is it going to be like fragmented?
Yeah, fragmented, so to speak.
Yeah.
This way, the two slits will interfere with one another, and so now you'll see a pattern of much more closely spaced interference maxima, but they'll still be modulated by the overall diffraction pattern of the slits. They're identical slits, and so they have the same diffraction pattern, and we're far enough away that their diffraction patterns pretty much overlap one another, and so you'll see interference maxima, but they won't all be the same brightness because of the diffraction of the light from the individual slits. And so I will, everybody come as close as you can here while I'm doing this. So I will turn this, and now both of the slits are illuminated. And what was a single broad bright stripe before, there's lots of narrow bright stripes within it. And those are the interference maxima of the two slits. So come on, get close enough to really see that because they're pretty close together. Get like right up here where parte is so that you can all see it nicely. Because I want, and then notice that again, there's that modulation by the diffraction pattern. So the secondary maxima also have those interference strips, so to speak, across them. Wow, what does that make you want to say? Ooh. Ah, you know, me too. I have no idea if this is visible to, and let's see. Let me see if I can zoom in well enough here that our audience at home, so, oops, no, don't close the lens. Audience at home can see here, I'm going to zoom in. Zooming. Trying to get as close as I can here. Yeah, there it is. There it is. Look at that, Esmeralda. Isn't that amazing? I can hear you saying, ooh, ah. Look at all those narrowly spaced vertical strips within the broad diffraction maximum. Whereas when I move the slit blocker and block one of the slits, oh, those just disappear. Oh, I blocked them both there. Those just disappear, and we only see the broad maximum. But then if I expose both slits again, here we go. Oh, there it goes. Oh, many strips. You know, y'all can just watch this later so as you say, ooh, ah, repeatedly as you marvel at what's going on here. And again, we'll do it with a photomultiplier tube that will detect individual photons going through from that dim light bulb with a green filter in it so that we have relatively monochromatic single wavelength light from it. It'll be a narrow range, but a narrow range so that it'll all be about the same wavelength. And you'll see that even when one photon goes through at a time, you still get the interference pattern. And it's like, quantum mechanics is real! All right, that's our field trip. Any questions, comments, observations? All right, back to the salt mine. I mean, back to more exciting lecture learning opportunities here. Don't you wish you were in this class? Oh, no. Don't lie like that. All right, so first we'll talk about interference, and then we'll talk about diffraction. Of course, they're not really different things. Interference is just diffraction too. It's all the spreading out of light that's interfering from different parts of an aperture. So there's really no distinction truly. And yet we kind of say interference when we've got like multiple apertures and the light from them is overlapping and producing an interference pattern. We talk about diffraction for what happens from a single aperture, but it's all fundamentally the same thing. So let's talk about the two-slit interference pattern. Where we're not yet accounting for the effect of the finite width of the slits, that they have those diffraction lobes in the overall pattern and not just the interference right strips maximum. So two-slit interference. And again, am I right about this? And you did this in lab in 111.
but never really did it in class, is that right? So we probably haven't kind of studied this in detail in a class setting. So what we're going to do is, so in the experiment, what you're going to have is this little circular metal oxide plate that has two slits cut into it, two vertical slits. The laser light is going to go through those and produce the interference pattern. And what I'm going to draw here is the view from above. In other words, our eyes up here, and you take a slice through this, and we're just looking at this from above. So the two slits are just going to be two openings that I draw like so. So here's that plate, and let me do a better job than that. So there's an opening. Here's an opening. So those are the slits that we're seeing from above. Does that make sense? Seeing them from above. And so here's the slits. And we have an incident plane wave. So in other words, we've got a light wave coming in, and I'm going to draw. So you may know, light's an electromagnetic wave. So both the electric and the magnetic fields vary in space. And the simplest situation is a sinusoidal, all one wavelength, plane wave, where the wave fronts, the surface is a constant electric field, constant magnetic field all over them, are planes. So the electric field is everywhere constant in magnitude and direction on planes that are perpendicular to the board here. And so in my slice here, the planes are just these lines that I'm drawing. And these are all supposed to be the same distance apart. And I'm drawing dashed lines and solid lines to represent, if you will, crests and troughs, or electric field of maximum in one direction, electric field of maximum in the other direction, and then varying sinusoidally between them. And so these are incident plane wave fronts. That are going to impinge upon those slits and produce an interference pattern beyond them. Okay, what questions do you have at this point? It's important to be on the same page of knowing what this represents. So everyone, like this line here, really is a cross-section through a plane wave front, where the electric field is constant in magnitude and direction everywhere on that plane. And the dashed lines are where it's a maximum of the electric field in the other direction. And so you can consider those to be like the crests and troughs, if you will. And there's a sinusoidal variation in between. And so this whole pattern is moving like this, illuminating the slits. And then we're going to use what we call Huygens principle. Do you know what Huygens principle is? So it's named after the Dutch scientist Christian Huygens, who formulated it, and it can be justified by looking at the wave equation and looking at the Green's function solutions of it, if you know what those are. We're just going to take my word for it that this works and it can be mathematically justified. Huygens was just kind of intuiting this idea and showing that it produced what we observed. Christian Huygens, by the way, also discovered the moon Titan of Saturn with a telescope, and so the probe that went to the surface was called the Huygens probe, as a matter of fact. And he might have even been the first to identify the rings for what they were. Galileo saw them, but he thought it was a triple planet because his telescope wasn't good enough for him to understand what he was looking at. I know Cassini found the big gap in the rings. I don't think Cassini found the rings, though. The mission itself was called Cassini with the Huygens probe. Anyway, Huygens principle. I'll write that over here because I want to draw some more diagram there. Huygens principle. And by the way, that's my attempt to say his name. It's a Dutch name. I played audio of Dutch people saying his name, and I decided Huygens is as close as we're going to get, because they're like, Huygens or something. Okay. Huygens principle. Each point on a wavefront serves as a source of spherical, actually I say kind of like hemispherical because they're only going in the forward direction, hemispherical secondary wavefronts, secondary wavelets or wavefronts if you like, that overlap and interfere to form the wavefronts beyond them, if you will. So in other words, the idea is we think of these slits being illuminated by the plane wave. Each slit, in the limit that were a single point, we would just have a nice spherical wave. When we get to diffraction, we're going to think in terms of spherical wavelets coming out of each and every point in there. If we think the slits are pretty narrow, we kind of draw something like this. So here's these secondary wavelets coming out of the slit on the top there. Same wavelength and frequency as the illuminating wave. So each one of them is doing this. And at a point like this, for example, the net disturbance would be the sum of the disturbances due to the individual slits. So you're adding the waves from the two slits together to figure out what the electric field looks like, or whatever disturbance you're looking at is at every given location. You can do this at every point in space, add the wavelets from the two slits together, and that'll tell you what the electric field or whatever looks like at that location. That's Huygens' principle. Again, you can justify it from the differential equations, from Maxwell's equations, and it's awfully close to being correct. Let's put it that way. The Green's function solutions are not quite, the amplitude varies with angle and so on and so forth, but especially if we stay not at too large an angles away from the center line, it does a great job of describing what's happening. Okay? So back here, we've got a screen, and again, it's really sticking into and out of the board. And we want to know, well, okay, if I'm smart, I'll draw the lines first. So here's some point P. And if I do this well, I will aim this and actually hit the screen back there. I probably should have drawn this, let them intersect, and then draw the screen where they intersect. So let's see how I do. I might be moving the screen a minute there. That didn't suck, okay? So there is a little part of the wavefronts from each of the slits heading out and meeting and overlapping and interfering at point P. And so, the further away you are from the slit, the closer those spheres, their radii increase, so a little piece of them looks more and more like a little section of a plane itself. So out here, if I kind of draw some wavefronts from both slits, it might look something like that. in the situation I've drawn, crests and troughs are shifted from one another. There's a phase shift between them. And so when they get to point P, they're not perfectly in phase with one another. And we'll get maxima where the two waves are in phase with each other. Crests overlap crests, troughs overlap troughs. And they'll completely destructively interfere when they're 180 degrees or some multiple of 180 degrees, like, some odd integer multiple. In other words, if the phase shift is an integer number of half wavelengths between them, they will destructively interfere. Crests will overlap troughs, the electric fields will be equal but in opposite directions, and they'll cancel one another. So we'll get bright spots. We get bright spots, interference maxima, when the waves from the two slits are in phase. And dark spots, interference minima, when they are fully out of phase. And at a general point, they won't be either completely in phase or completely out of phase, and so you see a variation in brightness going from maximum to minimum to maximum to minimum. Those were those strips that you were seeing, those interference strips where you saw the bright stripes. The maxima, that's where the waves were completely in phase, and the dark points halfway between were where they're completely out of phase. What questions do you have at this point? Including, what? What is always entirely fair. Just being sure. Yes, okay. So, if they're fully in phase, the condition for that is that the path length difference from the slits to P, the difference in those path lengths is an integer number of wavelengths. Because if you shift one wave, a whole wavelength relative to the other one, they're back in phase. The crests are overlapping the crests, the troughs are overlapping the troughs. If you shift one wave by 2 wavelengths compared to the other one, they're back in phase. So, in phase, the path length difference, the difference in distance from each slit to P, is an integer number of wavelengths. Half-length difference from the slits to P is an integer number of wavelengths. shift sinusoids by one wavelength relative to one another, and they're back lined up with each other. Now, we're ignoring the fact that the waves become the light becomes dimmer the further away you are from the slits, and so if they're not exactly the same distance from both slits, the light from one slit's a little the light from the far slit is a little dimmer than the light from the near slit. But that's going to be a very tiny effect if the screen is far away, so we just ignore that. We just ignore that. In the limit that the screen gets infinitely far away, that becomes negligible. In practice, if the screen is a lot further away than the distance between the slits, we can ignore that. Out of phase, I'm just going to say PLD, the path length difference, is a half integer number of wavelengths. Where in physics, a half integer is 1/2, 3/2, 5/2. It's an odd integer times a half. So in other words, lambda over 2, 3 lambda over 2, 5 lambda over 2, etc. As opposed to lambda, 0, comma, lambda, 2 lambda, 3 lambda. That would be the list for in phase. And the fully out of phase list is half lambda, 3/2 lambda, 5/2 lambda, because then they'll have 180 degrees phase shift essentially. The crests and troughs will overlap, and so the electric field wherever will be equal and opposite from the two slits, and they'll cancel one another. Will cancel. So that's our condition here. This is what we're after. So now I'm going to redraw the picture again so that we can zero in on what we need. So here again, put it down here, kind of same one. Okay, so. All right, so here's the, I guess I'll get fancy and make it look like, here's this thin metal sheet that we cut the slits out of. And now we're going to say the distance between the two slits, we're going to call that D. Later we're going to call A the width of the slit. We're not worried about the width of the slit. That's where the diffraction lobes will come in, but we're ignoring that for now. So D is the distance between the two slits. Okay. Here is a portion of the waves from each slit heading off into the distance. Damn, I'm good today. I feel like Dr. Trees or something. I'm channeling Dr. Trees. Because Dr. Trees is the only person somebody heard me say this before. I sometimes forget that it is much better to first draw your circle and then locate the center than it is to first draw the center and then try to draw your circle around it, because as you can see, I did a better job of centering in that case. And so Dr. Trees, I feel like he's got a built-in compass. I mean, he just draws the center and draws the circle around it, no problem. It's like, what's up with that? Anyway, I'm channeling Dr. Trees today, getting those things to stay straight and go pretty nicely there. Not perfect, but whatever. Kind of hard to do on a blackboard. So there's our screen again. Here's our point P that we're interested in. And we're going to say that the center line, if you will, goes from halfway between the slits to the screen. And angle theta, okay, well, that did kind of curve there. Here's the real test. Okay, it is going to fail. I'm going to try to go right down the middle of the channel. It did curve at the end, so I'm not as proud as I was from over here. I'm not quite as proud of myself as I was before. Your picture will be perfect, especially if you're using an iPad and just corrects everything. So there's the center line. there's the line from halfway between the slits to point P. And we're going to call this angle right here between the center line and point P, as seen from the slits, that's angle theta. And we're going to say that the distance from the center line to point P on the screen is y, because why not? And we're going to say that the distance from the thingy that has the slits in it to the screen, that's going to be capital L. That's that length, capital L there. And if we think, well, as L goes to infinity, and in practice it needs to be way bigger than D. So we're not there yet really here, right? That L is bigger than D, but not way bigger than D. As L goes to infinity, the lines from the slits to P get more and more close to being just parallel to one another. So in that limit, we can just draw them as parallel. As L goes to infinity, the lines from the slits to P become parallel to one another. Parallel to each other. So we can use this diagram to find the path length difference. To find the PLD as a function of theta. So here again is our distance D between the slits. And here's our parallel rays, both heading to the same point P. So 2P, way off in the distance somewhere, those two parallel lines both heading to P. There's that angle theta again, because in this limit, if all the lines are parallel, theta becomes the angle of every one of these lines from the horizontal. So there's theta. And then I can make this little right triangle right here. Drop that perpendicular like that from one ray to the other. Draw a perpendicular from the location of the ray at the top slit. Draw a perpendicular to the ray coming from the bottom slit. And then, well, if this angle's theta, from this as being a right triangle and all that, right? Well, from this being a right angle, if this is theta, that's 90 minus theta right there, but then this is 90 minus theta. This angle right there is also theta. Those angles are both theta. And that little segment right there, from the lower slit to the intersection of the perpendicular from to that intersection with that perpendicular I drew, that's the extra distance that the light has to travel from the lower slit compared to the upper slit in going to point P. In this limit, this is the path length difference right there. Does that make sense? It's crucial to buy into that. Because the rest of it, they're all going the same distance the rest of the way to P. So this is the extra distance right there that the way from the lower slit has to travel compared to the way from the upper slit. And then, well, good, we've got a little right triangle there, and its hypotenuse is D, and the PLD is the side opposite angle theta in a right triangle whose hypotenuse is D, or in other words, the PLD is equal to what? There's D, the hypotenuse, there's angle theta, this is the side opposite. So if you soak a toe in this sucker right here, this distance is, yeah, right, the PLD is just D times the sine of theta. The distance between the slits times the sine of that angle theta is the path length difference. And if that is an integer times lambda, you get a bright spot. Those are the thetas where you get bright spots, is where d sine theta is an integer times lambda. Ta-da! So we thus get bright spots on the screen corresponding to constructive interference when d times the sine of theta is equal to lambda, m lambda, where m is 0, 1, 2, etc. Makes sense? What questions do you have? D sine theta is an integer times lambda. Actually, I should really just take it too. In some sense, if you just care about the path length difference, you don't care if you're on plus or minus. If you go on the other side and you just, okay, you could just say, oh, I just care how many wavelengths path difference are. But if I'm standardizing on like above, like if it's the path length from the lower slit minus the upper slit, well, if you go down here, it's the other way around, right? Then it's the lower slit that's closer. And in that case, the path length difference becomes negative. The path for the lower slit minus the path for the upper slit is negative because the path from the upper slit is larger. So the most general way to put this would be dot, 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 minus 2, minus 1, 0, 1, 2, dot, 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 dot. So just some integer number of wavelengths, could be plus or minus depending on which side you're on of the maximum, of the central maximum. The central maximum is one in the middle of the pattern. And what value of m? For the very central maximum, right along the midline there, the bright spot right along the midline, what's m in that situation? Is there a path length? Is the path different? Is the path length different for the two slits in that case? No, so what's m? 0. M equals 0. I have here, m is called the order. As m equals 0, the adjacent maxima on either side of it equals plus or minus what? 1, right? Plus or minus 1. In other words, the first time I'm going to get a bright spot, here there's no path length difference between them. The first time I get a bright spot will be when there's 1 path length difference between them, 1 wavelength path length difference. The next time will be 2, the next time will be 3, and so forth. The next 2 on either side. M equals plus minus 2, etc. So if I sketch the interference maxima, here's a series of maxima, a bunch of interference strips. If this is the one with m equals 0, then it's up to us which side is plus, which side is minus. But if we say going to the right here is the plus side, we're arranging the slits so we make that the positive side. There's plus 1, minus 1, plus 2, minus 2, plus 3, minus 3, and so forth on both sides. I think it's pretty cool, right, when you think about it. So, does anybody know what range of wavelengths are human eyes able to see? About what, in terms of nanometers? Anybody know?
6,000 to 8,000?
Not in nanometers, and not quite. So if we use angstroms, it's in the thousands. Like angstroms is a tenth of a nanometer. In terms of nanometers, human vision goes from about 400 nanometers to 700 nanometers. 400 to 700. Of course, you know, for me it might be 413, and for you it's 398 or whatever, right? But about 400 to 700. What do different wavelengths correspond to subjectively to us? They're different colors, right? They're different colors. Now, most colors are blends of wavelengths. So if you see monochromatic light, right, a single wavelength, that's the equivalent to the sound version of a pure tone, like a 1 kilohertz pure tone. My voice doesn't have a wavelength and frequency, it's a blend. If you and I sing the same note, they sound different because you have a different ratio of the harmonics to your fundamental than I do, because your larynx and vocal cords are different from mine. And so similarly, you know, like I'm wearing this blue shirt, that's not one wavelength in hearing, but the colors of the rainbow are essentially the pure tones of light. And do you know 400 is that? Well, first of all, what are the colors of the rainbow? What do we say for what it's red? What's next? Red, orange. You're missing one. Red, orange, yellow, then green, then blue, then stop it! No, no! Yes, then people will sometimes say indigo, which is a J. Crew color, bluish purple. Stop it! So yeah, they're right. The mnemonic is Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. I maintain that indigo is just there to make it more pronounceable. So I'm all for Roy G. Biv, red, orange, yellow, green, blue, violet. Red, is that the 400 end or the 700 end? No, other way around. Red is the 700 end. Red is the 700 end. Violet is the 400 end. Longer wavelengths are red, orange, yellow, and shorter wavelengths are green, blue, violet. And so that's being illuminated. We had a red laser there. It turns out its wavelength's about 670 nanometers, 670 billionths of a meter. And I think it's cool to realize that, okay, so those first stripes on either side, the path length difference over about a half meter of distance there, the path length difference was like 670 nanometers. And you're able to see that, the fact that there's a 670 nanometer difference between the path lengths. think it's cool that you can see that. I've always appreciated that. We'll take a break in a moment. I've told this to some of you before. As some of you already knew, my feelings towards indigo, right? Some of you know that I like learning German. There is a German band that I like called Silbermond, means silver moon. And they have a song where when I heard it, I realized what the German word for indigo is, because the lead singer starts going, indigo, indigo, oh. It's indigo too in German as well. So I can hate it in both languages, as a matter of fact. And then, yeah, I've told some of this too. It's very amusing to me that Germans cannot pronounce the English word for squirrel, and English speakers cannot pronounce the German word for squirrel, because Germans tend to go like squirrel. It's really hard for them to say squirrel. And it's hard for English speakers to say Eichhörnchen, which is the German word for squirrel. So squirrel in both languages is hard for speakers of the other language to pronounce. Very entertaining. I saw a video of Germans. So essentially get dark spots halfway between the bright spots. And you're going to be quantitatively measuring brightness as a function of position. So we need to be able to be quantitative about that here. We need to come up with a formula for that, which again we're going to have to later modify to account for diffraction as well. So the phase difference between the waves from the two slits at P is, we'll call it delta, like that, small Greek delta, equals, well, that'll be the phase shift in one wavelength we're going to do this in radians times the PLD in terms of wavelengths. So what is the phase shift corresponding to one wavelength in radians? One wavelength is how many radians? It's one full cycle. How many radians in a full cycle?
2 pi.
2 pi, right. So that's going to be 2 pi times the path length difference in terms of wavelengths will be the PLD divided by one wavelength. That's how many wavelengths of path length difference there are. But PLD, we said, is d sine theta. So that difference in the phase between them will be 2 pi over lambda times d sine theta, which we'll draw a box around and we're going to come back to in a little bit. So 2 pi over lambda times d sine theta will be the phase difference between the two waves at any given point. So that's it as a function of theta. maybe? Let's all take a pause for rides. Although I have a feeling he'll come back and that's what happened. So,
I'm back for you.
with food that, and I'll be like, damn, you got food and I don't. Okay. All right. Yeah, my wife plays this game on her phone, like, you know, it's like making all this stuff in the bakery, and I'm like, that makes me want all those things, you know? It's like, I want those brownies and those pies and all this kind of stuff. Terrible. Anyway, so it'd be rather inconvenient to try to measure theta directly. What we can readily measure is y, the distance along the screen. And so let's put theta in terms of y. From the diagram, we have, ooh, look at this. We got ourselves a big old right triangle here, and sine theta, well, that's not what I say, tan theta, tan theta is y over L. Right? Tan theta is y over L from that right triangle. We have tan theta is equal to y divided by L. But recall that for small theta, we have that tan theta and sine theta are very nearly equal to one another, because if theta is small, the hypotenuse of that triangle and L are practically the same length as one another. And so we can say, to an awfully good approximation, sine theta and tan theta are the same. And so d sine theta, which is so important to us because it's the path length difference, to an awfully good approximation is just d times y divided by L. Okay, I hope I don't regret this, but I'm going to erase my beautiful diagram here, but it's always in your notes. So, goodbye. 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 I can control my emotions here. All that work and love and care I put into drawing, it's just all gone. Gone. So ephemeral. Thus, to a good approximation, we get maxima for dy over L is equal to an integer times lambda. So y sub m, the location of the nth maximum, is m times lambda L over d. That'd be our predictions of where the maxima are on the screen. So, for example, we could measure where the maxima are, and if we measured the distance from the slits to the screen, and we know the slit width, we could calculate lambda from that. We could use this to determine the wavelength of light. I wonder if I'm going to have you do something like that during that lab. I don't know. What do you think? Might I do that? Never, never would I do that. Of course not. Why would I do such a thing? What is this, a serious physics lab or something? Exactly. Yeah. So Im, of course, here is the distance of the nth maximum from the center of the pattern. So distance of the nth order maximum from the center of the pattern. This is the way that we find, like wavelengths of light typically with this kind of measurement. I mean, you can't exactly, let's take a meter stick and try to measure those light wavelengths, but this is where you do it. This is where you define those wavelengths. I mean, it's hard to get light to sit still for you, and then and then the distance between successive maxima Ym plus 1 minus Ym. Why, that's delta y equals lambda L over d. That's typically what you use to figure out what the wavelength is, for example. Just measure how far apart the maxima are from one another and plug into that formula after solving for lambda. Questions, comments, observations? Okay, but why, Physics 111 lab, you might do that. You'd find out how far apart are the maxima, I'll measure it with my ruler, and use that to find the wavelength. But this is not Physics 111, this is Physics 245. So you'll quantitatively measure the intensity variation, and then you're going to fit a curve to it. You're going to fit a product of the sine and the cosine that describes the overall intensity pattern when you combine the effects of the interference between the two slits and the diffraction from the slits. There'll be this somewhat complicated, not horribly complicated trig function that you will fit to your measured intensity pattern in order to determine the wavelength. It'll be cool. But that means we should know where that's coming from. What is this intensity pattern? How do we expect the brightness to vary with position on the screen? First, we'll do it just for the interference, and then we'll toss in how diffraction works. That gets a little bit trickier to calculate. Not horrible, but a bit fancier calculations are needed. So, finding the intensity as a function of position along the screen. Again, with the laser, you'll be using a diode, and you'll be reading the voltage on it, which is proportional to how intense the light is. But with the light bulb source, you'll be using counts from the photomultiplier as the intensity. Finding the intensity as a function of position along the screen. So time to have fun with trig identities. I'm terrible at remembering trig identities. I always have to look them up. I have a mental block for like sine alpha plus sine beta is what? I don't know. What the phase difference between the waves? from the two slits B delta, like we called it before, from the two slits at point B B delta, that's what we're calling that. So then let's write down what the two light waves look like. The two light waves can then be represented by E1, the electric field from the first slit. And we're not going to worry about making it a vector. We'll just assume that, well, if it's a plane wave, the two electric fields will be in the same directions from the two slits. So since they're in the same direction, we don't need to worry about angles between the vectors or anything, so we just treat everything as scalars. E1, we'll say that's A naught, and we'll say sine omega t, right? Because it's a sinusoidal variation in time with angular frequency omega. And E2, because of the phase shift, will be A naught sine of omega t plus that phase shift. So it'll be advanced or retarded in phase compared to the wave from slit 1. So A naught, here's the amplitude. And we are choosing to start the clock, so to speak, at a moment when E1 is equal to 0 and increasing. In other words, there could also be an arbitrary plus phi attached to both of these, where there's a phase shift at time 0, but let's just start the clock at a moment where we can just say t is the argument for the first one and not needing a phase shift there. It's up to us when we start the clock. So here E1 and E2 are the electric fields. Of the waves from the two slits. We assume they have the same amplitude because the PLD is small compared to the distance from the slits to the screen. We mentioned that before. In other words, sure, the wave from the closer slit will be a little bit higher amplitude, but the difference in distance is so tiny, we can ignore that. The phase difference is much more sensitive to the path length difference than the amplitude, because the PLD is small compared to L, the distance of the ball. I'll just be more specific. Compared to how far the slits are from the screen. So here we are still again talking about the far field. If you looked at the interference pattern close to the slits, the near field, then you wouldn't be able to get away with all this. We wouldn't be able to say d sine beta is m lambda. We'd have to account for the fact that the waves weren't parallel. We'd have to account for the fact that one of them was closer to the slit, closer to the screen than the other. The near field calculations are harder to do, but we're out in the far field where we can keep things simple. And that corresponds precisely to if you have the card, when it's close to the slits, the pattern looks different, and as you move it along, it keeps changing, and when you're far from the slits is when you get to the limit that we're talking here. When you're very close to the slits, the near field diffraction pattern, well, that's when you just get the two stripes, one from each slit. And as you move further away, it gets more and more complicated, and it's difficult to calculate what it is at some intermediate distance. You don't get to make the approximations. When you get far enough away, we get to make all our approximations, that the two amplitudes are equal, that delta is just proportional to d sine theta, all that kind of good stuff. What questions do you have? Well, let's continue then, enjoying this journey here. I think this is fun, so I order you to think it's fun too. Then the total electric field is, well, electromagnetic waves obey this principle of superposition, that you get to just add them together at every location. So it's going to be E equals E1 plus E2 equals A naught sine omega t plus A naught sine of omega t plus delta. As you learned in kindergarten, sine alpha plus sine beta, there's a trig identity that says that that is 2 times the cosine of 1/2 times alpha minus beta times the sine of 1/2 alpha plus beta. I had a professor in grad school, Peter Freund from Austria. He was an opera singer. He sang opera for fun. And he was very fond of saying, as you learned in kindergarten, and we all figured he probably did learn that in kindergarten. Brilliant theoretical physicist. I think I've told some of you the story of he was teaching us graduate mechanics, and he starts using all these properties of vector spaces, and then at one point he says, oh, I'm sorry, I've been using properties of vector spaces without saying what a vector space is. Is there anybody who doesn't know what a vector space is? And one of my friend Mike timidly raises his hand and says, could you remind me? And Peter Freund, in a very Peter Freund way, says, it's simple. It's just an abelian group with an addition defined. And then he just kept going from there. So that was one of those classes where it's kind of its own prerequisite. But there are some folks that are kind of like that. So in any case, as you learned in kindergarten, and then since I like puns and so forth, see if you get this. I have to remember how it goes. I probably won't say it quite right, but if you get it, just let me think here. Like something like, when you compare kids in America and Germany, what's true is that German kids are always yeah, because the plural of das Kind is kid in German, and the plural is Kinder. So German kids are always, you have to kind of write, Kinder doesn't work spoken, right? But if you write it, it looks like kinder, and they're like, it's the German word for children, so German kids are always children. Okay, so moving on. Okay, so we're using our kindergarten trig identity, and here we'll have alpha being omega t, and beta being omega t plus delta. So we just plug those into our trig identity, and we get that E is 2a naught times the cosine of minus 1/2 delta times the sine of omega t plus 1/2 delta. Right, because with those alpha and beta there, then alpha minus beta is omega t minus delta, so you get half of minus delta for the first term, and for the other one, we're going to get omega t plus delta, so in other words, 2 omega t plus delta, and when I throw that 1/2 in there, it becomes omega t plus half delta. So a naught sine omega t plus a naught sine omega t plus delta can also be written as 2a naught cosine of minus half delta sine of omega t plus half delta. But wait a minute, what can I say about the cosine of minus a thing? Almost. It's not minus cosine the thing. It's cosine the thing. Yeah, cosine the thing. Right. The way I remember things like that, I'm terrible at remembering trig identities. But when I want to know, like, wait a minute, is it cosine of theta? Cosine of minus theta is what compared to cosine of theta? I just mentally think of the plot of cosine theta, right? Here's theta, here's cosine theta. And if I go the same distance on either side, I'm back to the same y value. So therefore, cosine of minus theta and cosine of theta are equal to one another. Right? So I can always remember it just by thinking of the plot. Similarly, if you plot the sine function, right? It's so if I go the same distance on either side, then I flip signs. Because sine of minus theta is minus the sine of theta. So that's I think the best one. That's what makes me always never forget which way it works. Okay. So in other words, we can say that E is square brackets 2a naught cosine half delta times sine of omega t plus half delta. And if you want to put parentheses around the half delta, strictly speaking, you should. But we often don't. So notice that the phase of the resulting wave, 1/2 delta, the phase shift of the resulting wave is halfway between the phases of the two waves that combine. In other words, this one has 0 as the phase shift, this one has delta as the phase shift, and the combination has half delta as the phase shift. So the phase of the resultant wave is halfway between the phases of the two waves. And more importantly, its amplitude is 2a naught cos half delta. Because it's that amplitude that's going to tell us how bright it is. And its amplitude is, oh, we'll call it A naught prime equals 2A naught times the cosine of 1/2 delta. 1/2 delta. Okay, I'll stop for a minute, let you catch up. What questions do you have? Fun with trig identities. Can't remember them, but I still think they're fun, personally. And if you go to Wikipedia, they have nice pictures which show where they all come from. Stuff like that. Yes?
If A naught is the amplitude of each of the waves,
Yeah.
like, is the amplitude of the original source to A naught, or
No, the original source is amplitude of A naught. And the point here is that with constructive interference, you get twice the amplitude of the original wave. And I'm going to say this again, but intensity is proportional to amplitude squared. So the interference maxima are 4 times brighter than the wave from either slit by itself. If you just had one slit illuminating, the interference maxima are 4 times brighter than that. But the minima are 0 times brighter, right? The minima, there's no intensity there. And so we haven't violated energy conservation or anything like that. What we have done is redistributed energy in space. The total energy stayed the same, but we've redistributed it. There's some places where we concentrated it and some places where we diluted it. That's what it comes down to. This happens with sound waves too. You can get, if you fire 2 speakers, especially at low frequencies, you can notice this. If you walk around, you can hear interference maxima and minima between the 2 speakers. And where you're at the maxima, it's louder than either speaker by itself will be. If you turn off one speaker and then turn it back on at an interference maximum, it becomes 4 times louder than either one speaker by itself is, not twice as loud, because it's the amplitude squared that tells you the intensity, it tells you how loud the sound is. But at interference minima, it's 0, it's gone away. If you have noise canceling headphones, what they're doing is they've got a microphone that picks up the outside sound and they run it through a little amplifier that reverses the signal so that your earbuds are creating a sound wave which is 180 degrees out of phase with the sound wave at their microphone, with the sound wave that would be hitting your ear. And so to the extent, some are better than others, but the idea is you're essentially canceling the external sound wave and it goes away. So you don't hear as well the stuff on the outside. Are you violating energy conservation? No, it's not just disappearing. There's other places nearby where it got louder, but those aren't inside your eardrum. And so you only care what you're hearing inside your eardrum. Fun with physics! Tell your friends. All right? Special cases. Delta is 0, plus or minus 2 pi, plus or minus 4 pi. In other words, full wavelengths of shift, right? In terms of delta. In terms of wavelength, 2 pi is 1 wavelength, 4 pi is 2 wavelengths. In that case, if I take the absolute value of A naught prime, it's 2 times the absolute value of A naught, because in those cases, cosine is 1 or minus 1, right? And in that case, because we only care about the amplitude, the magnitude of it, you get twice the amplitude of the incident wave. That's total constructive interference. At the interference maxima, the electric field amplitude is twice the amplitude coming from either slit by itself. Total constructive interference. And if delta is plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, etc. Well, that's when they are completely out of phase with one another. In that case, if you put in pi, for example, cosine of pi over 2 is equal to what? Yeah, 0, right? Again, think of these plots again, right? In other words, pi over 2, pi, 3 pi over 2, right? When you're trying to figure out this, just think of the plot in your head. Cosine of pi over 2 is 0, because look, that's where it crosses the axis the first time. What's the sine of pi over 2? Again, think of these plots. Mentally have those plots in your head when you're trying to remember what is the sine or the cosine of those basic angles like that. Having the plot in your head is the best way to do it rather than, I'm going to memorize that the cosine of pi over 2 is 0. No, think of the plot, think of the plot, think of the plot. By the way, the plot, you should think about it. Right? So here, these are all the values where cosine is 0. Cosine of half delta is going to be 0 for those. So in that case, A naught prime is equal to 0. No signal. Total destructive interference. Totally, dude. Total destructive interference. You gone. But now we know how to figure out what the intensity is anywhere else too. Whereas neither fully constructive nor destructive, we got an expression for the amplitude anywhere, but that tells us the intensity anywhere. So the electric field is actually varying extremely rapidly if you're illuminating with light waves, right? Light waves have frequencies on the order of like 10 to the 14, 10 to the 100 trillion hertz or something like that. I have to think about it. It's huge. We can't follow that, right? When you measure the brightness of a light wave, do you see it flickering as the amplitude goes, as the electric field goes from 0 to maximum to 0 to maximum in the other direction to 0? Does your eye see it flickering trillions of times? No, it doesn't. You just see an overall brightness, right? So this piece isn't really going to matter. Interesting that the phase is halfway between them, but this is just going to be this rapid variation that our instruments or our eyes are not going to follow. All it cares about is the amplitude. Now, it turns out the time average of sine squared is a half, and so that would be there too. But the intensity is proportional to the amplitude squared. There'd be a half there. There'd be like epsilon naught or whatever for ENF. What really matters is it's proportional to the amplitude squared. So the intensity which would be power per square meter of detector surface. Detector is going to be a very tiny fraction of a square meter here, but in other words, the SI units of intensity are power per square meter. What are the units of power in SI? What are they? What's energy in SI? Oh, so precious. Energy in SI, the SI unit of energy, so precious. It's the joule, right? What's the unit of time? Second, right? What's a joule per second? What is a joule per second? Why, it's a watt! I did there, right? So in other words, this is going to be joules per second per square meter, which is watts per square meter. And the photodiode voltage is proportional to the wattage falling on it. So it's measuring what amounts to intensities for you. We're not dividing by the area of the surface or whatever, it doesn't matter. multiplier if it's the same for all of these. So the intensity is proportional to the square of the amplitude all. The intensity is some constant times A naught prime squared. So that'll be constant times 2A naught squared times cosine squared of half delta, because of the fact that A naught prime is 2A naught cosine of half delta, so you'll get constant, I guess it's constant squared if you want, times, still just constant. Okay, so it's constant times 2A naught squared times cosine squared of half delta. Quick, what's 2 squared? 4. Ah, and the president's a genius. 4 times constant times A naught squared times cosine squared of half delta. But let's call that I naught, the intensity from either slit by itself. Because each slit is producing light on the screen with amplitude A naught, so that constant times A naught squared should be the intensity either slit by itself is producing. So we can say I equals 4I naught, how much I get from one slit by itself, times cosine squared of half delta. So at the maxima, the intensity is 4 times what either slit by itself would produce. At the minimum, it's 0, as we already mentioned. Okay, so we're almost done with constructive interference, setting up Thursday's exciting episode, diffraction. I know you can't wait, but you're going to have to. But it gives you something to live for over the next few days, so keep that in mind. Right? But let's finish up this to make a happy coda. So, since we found before delta was 2 pi over lambda d sine theta, which is an awfully good approximation. Well, even this was an approximation, but it's a good one if you're far from the slits. Well, that was 2 pi over lambda, and then we found that d sine theta was d over L times y, to a mighty good approximation. We have our expression for how bright we will see as a function of y, as a function of position along the screen. I, as a function of y, should be 4I naught times cosine squared of pi over lambda d over L times y. And that's part of the function that you'll be fitting to your measurements. Your micrometer is going to tell you y values where you are. you'll have to say, you replace this with y minus y naught. In other words, you'll find the location of the central maximum. And when you've got diffraction included, the central maximum is brighter than all the others. If it's just interference, they'd all be equally bright. But with diffraction included, the central maximum is easy to locate because it's brighter than all the others. And y is relative to the central maximum. So if your micrometer is just reading y values, you want to subtract off y naught to get relative to the central maximum. This will be part of the function that you'll fit to your data to figure out what the wavelength is. And if we imagine plotting this, then here's I as a function of y, the y-axis. It's cosine squared, right? So cosine squared is kind of a distorted cosine that doesn't go negative and has two maxima for every period of the cosine instead of just one. So we get something that looks kind of like this. It makes that weird sound as you plot it. And this should be all nice and symmetric, so make yours better than mine. And so that's for I naught, the maxima for I naught intensity. And in terms of y, the other maxima are at L over d times lambda, 2L over d times lambda, etc. Oops. And on the other side, at y equals minus L over d times lambda, and minus 2 L over d times lambda, and minus 3 L over d times lambda. So if we didn't consider diffraction, we would find a prediction that as we move that slit along, that we get this cosine squared variation of intensity with position. When we include diffraction, it will be modulated with an envelope, and so it's going to be cool. You're going to make a plot that looks basically something like this. And you'll see that if you've done it right, it'll fit the predictions beautifully. You'll fit a function that, and like, oh my God, I believe in physics now. Not that you did before. You should be like, wow. And then I'm going to do a photo multiplier too, and I'm going to get the same thing, and it's going to work with that too. It's going to be like quantum. Oh my God, physics is amazing. Things to look forward to. Have you picked up on that I like that experiment? Because I do.